To design an aircraft, engineers must calculate the exact pressure and velocity of the air interacting with every inch of its surface. But standard rigid body physics, like Newton's F equals ma, isn't enough on its own. You can't just track the trajectory of a single solid object. Gas is a continuous, squishy, deformable medium that splits and compresses as it moves. To model this, we must build a specific mathematical framework grounded in 3 absolute physical axioms: the conservation of mass, the conservation of momentum, and the conservation of energy. In the previous chapter, we used the hydrostatic equation to establish the baseline static density of the atmosphere, represented by the Greek letter rho. Now, our objective is to take that static mass of air and mathematically force it into motion. Translating basic physics into fluid dynamics means we must stop looking for solid masses to track and start analyzing the invisible geometry of the flow itself. This is a flowchart mapping the foundational structure of basic aerodynamics to orient our analysis. Right below the root, the discipline splits into 2 distinct paths: flow with friction, known as viscous flow, and flow with no friction. That frictionless path is called inviscid flow. It is a theoretical idealization where we assume the internal friction of the fluid is exactly 0. By deliberately ignoring friction, we simplify the physics just enough to isolate and uncover the core rules governing pressure and velocity. We start with our first axiom. In a steady fluid flow, mass is neither created nor destroyed. To measure this, we defined a stream tube. This is an imaginary boundary made entirely of parallel streamlines that the fluid is physically incapable of crossing. What goes in one end must come out the other. If we look at the cross-section at station 1, we can define the volume of fluid sweeping past this point over a specific duration of time. That swept volume is the area of the cross-section multiplied by the fluid's velocity multiplied by time, dt. To find the actual mass of that fluid element, we multiply that swept volume by the fluid's density, yielding dm equals ρ1 times a1 times v1 times dt. To convert this localized mass into a continuous mass flow rate, we divide by time. The dt variables cancel, leaving density times area times velocity. Because mass is conserved, the mass flow rate entering station 1 must exactly equal the mass flow rate exiting station 2. In any enclosed flow system, a change in cross-sectional area demands a proportional change in either the velocity or the density to prevent mass from vanishing. Let's be clear about physical reality. All gases compress. The concept of a perfectly incompressible flow is a convenient mathematical myth. However, there is a practical engineering exception. For air traveling slower than 100 meters per second, the variations in density are so minuscule that they can be safely ignored. If we lock density in as a constant, those rho variables cancel out of both sides of the continuity equation, leaving us with area 1 times velocity 1 equals area 2 times velocity 2. We can apply this directly. Imagine air entering a convergent duct with an inlet area of 5 square meters at a velocity of 10 meters per second. We want it to exit at 30 meters per second. Since our target velocity of 30 meters per second is well below the 100 meter per second threshold, we are mathematically cleared to use the incompressible equation. By rearranging the variables, we calculate the required exit area to be exactly 1.67 square meters. As long as the airflow stays under that low speed limit, an engineer can perfectly control the velocity of a gas simply by changing the physical shape of the pipe. The continuity equation is useful, but it has a major blind spot. It tells us absolutely nothing about fluid pressure. To calculate the actual force pushing the fluid, we need to return to Newton's second law. Force equals mass times acceleration. We start by isolating an infinitesimally small cube of fluid moving along a streamline and mapping its spatial dimensions, dx, dy, and dz, along an x-axis. The force pushing on the left face of the cube is simply the static pressure multiplied by the area of that face. But on the right face, there is a resisting force. Because pressure varies across space, this opposing force must account for the spatial rate of change in pressure over that distance dx. By subtracting the right face from the left face, we calculate the net force acting on the element, leaving us with a negative pressure gradient multiplied by the volume of the cube. That negative sign has a specific physical meaning. A fluid will only accelerate forward if it is being pushed by a high pressure zone from behind into a lower pressure zone ahead. Next, we determine the mass of our infinitesimal cube by multiplying its density by its geometric volume. For acceleration, we utilize the chain rule to swap out our time variable for spatial coordinates. The rate of change in velocity over time becomes velocity multiplied by the change in velocity over distance. Now we plug these isolated components for force, mass, and acceleration back into Newton's classical equation. The algebra cleans up nicely. Because the volume terms appear on both sides, they cancel out entirely, leaving us with a minimalistic differential equation. dP equals negative rho times v times dv. This is Euler's equation. It dictates that an increase in velocity demands a proportional drop in pressure. Euler's equation is mathematically precise, but it has a practical limitation. It only calculates flow at a single microscopic point in space. The engineering goal is to predict the pressure difference between two entirely separate, distant points along the same flow path. To achieve this, we have to integrate Euler's equation from station 1 all the way down the streamline to station 2. Here, we must reintroduce the incompressible assumption. Because we are treating density as a constant, it is unaffected by the integral and can be moved outside the operation. Executing the integration produces a universally recognized formula, Bernoulli's equation. Bernoulli's equation functions as a strict conservation law. It allows designers to map the total pressure field surrounding an entire aircraft purely by knowing its airspeed. The intuition behind Bernoulli is straightforward. Because the two sides of the equation form a constant sum, a spike in velocity guarantees a drop in static pressure. But we have to respect the exact failure point of this equation. If the flow pushes past the 100 meters per second boundary, our core assumption of incompressible density completely shatters. Applying Bernoulli's equation to transonic or supersonic flight yields mathematically invalid and catastrophically dangerous predictions, because high-speed density becomes highly volatile. When density is a volatile variable, the basic tools of fluid mechanics alone lack the power to solve the system. To break the sound barrier, we must bridge aerodynamics with thermodynamics and harness our final axiom, the energy equation.